Hello and welcome to today's lesson on thin film interference. Today's goal, I can explain the concept of thin film interference and apply it to real-world applications, including the appropriate calculations. So, at some point in time in life, you have probably witnessed thin film interference and just not realized exactly what it is. And what it is, it occurs where you can see the whole color spectrum, like a rainbow pattern in maybe some gasoline that's spilt on the ground or some oil. And it creates an optical interference, and that's what we're really looking at today. So consider a horizontal film that's really, really thin. So we're talking about a very thin layer of either oil, gasoline, soap, and we're going to look at how it affects wavelength. How it affects the wavelength when light interacts with it. So, what happens is we get our incident ray. So we'll assume we're just going to look at one light ray coming in and striking the surface. So some of that light gets reflected. So your angle of incidence, theta I equals theta R, reflected light. Okay, so some of it's reflected. Now some of that light ray can be transmitted. So we still get the reflection, so some light rays gets reflected, but some can get transmitted into the new medium. All right, and from we can get a reflection back in the next interface. So right there we get some light gets reflected, which then would exit. And then you can still get some light then that is transmitted through. All right, that goes right through. So in the end, what ends up happening is exactly this. We get this light ray here. Some of the light ray will get reflected. And put my eye right here. So some of the light will go into the second layer. And inside that second layer, it may get reflected, and then it exits out and goes to our eye, and then some of that light is transmitted through. Okay, so what ends up happening is we see the light rays here are what we see. Now, because of that combination and that thickness there, this thickness here, it's going to affect how the light rays exit and cause constructive or destructive interference. And that's really, or essentially, what we are looking at today. So I have in the notes some examples. Probably didn't print very nice. They are color pictures though. But you can see that kind of rainbow pattern that is happening. Okay? Or that interference effect that's happening when light reflects off that thin film. Another one is Newton's rings. Okay? That differential, okay, that air gap that occurs back here, all right, there's a differential where that light takes time to get from this point, the reflected point, to this point. There's an extra travel distance, and that allows for constructive and destructive interference to occur. And that's what causes that ring pattern, because it is just rings of constructive and destructive light. So you're getting nodal rings from the destructive interference that's occurring. So properties of reflected waves. There are the two things we need to look at. So this is going back grade 11. Maybe talked about slinkies. So if we're going from a less dense medium, so I'm going to use a rope. So if I send a pulse down a rope, and this is my version of a thicker rope. Okay, my pulse is sent in that direction. So less dense or a lighter rope going to a thicker rope. What happens is we get a reflected wave, and in the thicker rope we get a transmitted wave, but of lesser amplitude. And this is what the result would be. And the free end, or more dense to less dense. So here's my thick. Okay, here's my thick pulse heading toward my lighter medium. What happens then is that thicker one will return on the same side. All right. So the pulse returns on the same side, and a pulse is transmitted. And we get that occurring. So that's what we got to keep in mind when we're doing this analysis of constructive and destructive interference. So I got a couple of scenarios to run through with you here. And the three scenarios are analyzing the thickness for our thickness of our films. So my note's kind of crammed all together, but this first one is supposed to be T is less than lambda, so the thickness of that film is smaller than the wavelength of light, which virtually means that the thickness of my film, so this thickness here, is essentially or approximately 0. This one, and your note hopefully printed out a little bit better. The next we want to look at is a quarter wavelength thickness, and then the thickness of half a light wavelength. All right. Now I'm going to kind of do this in two parts, and I'm going to do it with the first one with, so you can see my three mediums: air, film, air, and that's true all across. So this is kind of my N1, N2, and now it goes back to an N1, but I'm going to call it N3 for argument's sake. All right. So in the first situation, our light ray strikes the initial surface, and we get a bit of reflection. And you're going to have to bear with me here on my diagram skills. So I'm going to put a start line there. So what happens is I'm going to start this wave. I'm going to draw transverse wave. So I'm going to say that at that point, it is starting toward a crest. Now, the light that gets transmitted to the back film will reflect. And what we find here for this first situation, behind it, we find that N2 is greater than N3. So the N is the index of the refractive index for the material. So N2 is the refractive index of film, and air is N3. So in this case, the film is a larger index of refraction. So we get a situation where we have the film being more dense going to air, which is less dense. So if I go back a slide, we have this situation here, more dense hitting a less dense. So it's reflected on the same side that it struck. So that means that when it gets back and transmits out at this point up here, that it will be the opposite to the light that got reflected originally. Okay? All right, and the reason for that, oops. So our reason for that, okay, what we have is that light that transmitted to the back. So I'm talking about the interface right here. If it hit here as a trough, it got reflected as a trough. Okay, so that's why I have it heading and starting as a trough at that point. Okay, but up top here, we had air hitting the film. So the air hitting the film is less dense to more dense, which makes it return or go out of phase or be the opposite. So when it struck here, if it hit as a trough, and I'm assuming they both hit as troughs, and it's instantaneous because the thickness is almost 0, this one, it hit as a trough, it gets reflected as a crest, which means that they will be destructive interference for this situation. So this is destructive interference. All right. Now what happens if we increase the thickness? Instead of having a virtual 0 thickness, we do the same situation. So again, to forgive the drawing here, this is going to remain the same, right? Because it is a less dense to more dense. So again, we'll go with a trough. So it hits as a trough. So that means it's going to be reflected as a crest. Okay. The light that gets transmitted through will do the same thing. So we're assuming, again, happens almost instantaneously. Strikes as a trough. Okay. So it will be reflected as a trough. Okay. But because it's gone lambda over 4, or a quarter of the distance here, which means that if you go 1/4 that way and 1/4 that way, that essentially it's had time to do a half of wave shift. So that means that initially in the previous one, when there was no time lag, it would have came out as a trough, but because now it's a wave has occurred, it now becomes a crest, okay, because it's had that half extra distance to go through a whole phase shift, or travel a whole wavelength, half a wavelength. So if N2 is greater than N3, this will be constructive interference. All right. And finally, last one here. Now this time we're looking at lambda over 2, so it goes a half wavelength, back a half wavelength. So that means that's a full wavelength. So the situation here then becomes exactly like our first one, or essentially our zero thickness. So we'd have a crest, the wave that went through, excuse me, bounces back. Because it's done a whole shift, it really hasn't changed. So if I can draw this right, it's out of phase and tells me that for N2 greater than N3, we have destructive interference again. Okay, so that gives us a pattern. So if we go to the next slide, start with for N2 greater than N3, the pattern was, we'll start at the first one, lambda by 4, because we are looking at constructive interference. So if we look at this, constructive interference occurred here. So the first one was lambda by 4. The next one would happen at 3 lambda by 4. The next one would be 5 lambda by 4. And if we use, we're adding half a lambda each time. So mathematically, we're using an arithmetic sequence. I'm not going to go through and show you all of the math, but this is the formula that I would be using, where my A value is the first term. Here is my D value. So if I go through and do the calculation, we find that the thickness for constructive interference is going to be lambda 2n minus 1 over 4. Okay, so T is your thickness. N is your maxima number. Maxima number. Okay, so that is for when we have N2 greater than N3. So when we're going from a film back into air. If we look at the other side then, for N2 again greater than N3, again, the sequence for that one would be, if we look back, 0 lambda, we had destructive interference. So we had destructive interference for 0 and pi by 2. So 0 lambda, and then we got lambda by 2. The next one would be lambda, and so on and so forth. Again, if I use my arithmetic formula, we would find out that, again, we're adding by lambda by 2. The formula then would result in T equals n lambda divided by 2. Again, same thing for the thickness and maxima. I'm not going to rewrite that portion of it. Okay? Now, the trick to this is that it is not always going to be the case of film going to air. So I'm over here right now. So what happens when the N3 is actually the greater value? So what happens when N3 is greater than N2? All right, so I'm going to address that and finish this up in the next video.